today we are going to talk about our last aspect of the equilibrium constant K before we talk about it in terms of thermodynamics. And so today it is KSP. And so we call this the solubility product. All right. So in the past, we have said calcium fluoride, solid. Okay, if we put that into water and it dissolves, then we've got calcium ion and fluoride ion in solution. And we almost think of this as being like a strong acid or a strong base, just completely dissociates, and that's the end of the story. Well, that is not the end of the story when things dissolve. As a matter of fact, do you imagine that this one-way arrow is what the reality of this situation is? It is not. It is a two-way arrow. And so we're going to refine our thinking about solubility to reflect the fact that it is actually an equilibrium position. And so what we have to think about in terms of dissolving now is that when this reaches equilibrium, no more of the solid will dissolve. So when equilibrium is reached, no more solid dissolves. And basically what we can say at that point is that the solution is saturated, that no more is going to dissolve. So the solution is saturated. Let's write an equilibrium expression for it, for the dissolving of calcium fluoride. Alright, so our equilibrium expression is going to look like KSP is equal to where's the calcium fluoride in this thing? Well, it's solid, so it's not going to appear in the expression. Okay. Solubility product is an equilibrium so solubility product, KSP. It's an equilibrium constant and has only one value. At a given temperature. For a given solid. Okay, and so what I'm trying to say to you guys is that solubility, how much something will go into solution. Okay, so whether it's soluble or insoluble, honestly, solubility now, what we have to think of it as being is on a continuum. And that solubility is truly an equilibrium position. So it's not as simple as saying, oh yes, it will dissolve, or no, it will not. It's insoluble. But that it is a spot on a continuum in terms of equilibrium. All right, now one thing to keep in mind that could be useful at some point is that Q, the reaction quotient. Okay, so that is plugging in to the equilibrium expression, but plugging in with initial concentrations. If Q is greater than the KSP precipitate will, or in other words, the thing is going to be insoluble. The thing is going to be insoluble. All right, let's do a problem and see how this thing goes. They're actually pretty easy as equilibrium problems go. Okay, so calculate the KSP for solid bismuth sulfide, Bi2S3, which has a solubility of 1.0 times 10 to the minus 15 moles per liter at 25 degrees Celsius. Okay, so one of the hard things, or one of the different things about working KSP problems, so solubility problems, is the vocabulary, is the jargon. So what do all of these things mean? As we go through this problem, hopefully some things are going to be able to come clear. Okay, so the first thing is we need to write an equation that represents bismuth sulfide as it's going into solution. And so it's going to look like this. Bi2S3, that's a solid. And it is going to bismuth. Three plus, sorry. And that's going to be aqueous and sulfide, which is aqueous. All right, and 3. And we need 2. Okay. And as you can see, you guys, from already the equilibrium problems that we've done, the free responses that we've practiced, okay, you're given that thing. You're not going to have to write it. Okay, now the next thing we need to do is we need to write an equilibrium expression for this. So it is going to be KSP is equal to BI3 plus, and that quantity is what? Squared times S2 minus, and that quantity is cubed. All right, and there is our KSP. We are not, I mean, there's our equilibrium expression. We are not going to put the solid in there. Okay, now, I wrote it funny, didn't I? Because I left room for a denominator, which is not going to be there. So now the question is, how can we relate this number, this solubility, this, to what we have normally done with equilibrium problems, which is an ice diagram? What does solubility represent? What does solubility represent? What it represents is this. Solubility is equal to X. Okay, so in this case, that is the identity of X. It is whatever the solubility is that's given in the problem, and clearly we could go backwards from this as well. So now that we know that, are we going to be able, can we just go back to something we know? Can we go back to a nice diagram and fill in? Well, yes, we can. So let's do it. I'm going to erase this. And I'm going to erase this so that I can use this thing. Let's make it blue. Okay, I, C, E. Now, the thing about solubility is solids. Okay, and we have 0, and we have 0. Okay, we are going to gain what? 2x. We are going to gain 3x. So we are going to have 2x and 3x. So what are we going to do with them? We are going to plug them into the equilibrium expression, but we have x. Yay! So let's do it. Let's plug it in there. So we are going to have KSP equal to, now once again, let's write this thing so that we don't have any kind of confusion. So it's going to be, once again, BI squared cubed. So essentially, you guys, then we've got KSP equal to, from our ice diagram, what was that? That was 2 times x. 2x. 2x. So it's going to be 2 times 1.0 times 10 to the minus 15. And then what am I going to do to this entire quantity? Square it. Times 3 times 1.0 times 10 to the minus 15th. And what am I going to do to this entire quantity? Cube it. Because remember, you guys, I am plugging in from my ice diagram 2x, 3x, but do not forget, right, you're plugging them in and then you've got to square them as well. All right, so what ends up being our KSP? 1.1. Times 10 to the minus 73rd. Is that a large or small value for k? That's a pretty small value for k. That would be the smallest value of k we've ever seen. So equilibrium lies left or right? It lies pretty far left. And so would we expect much of bismuth sulfide to be dissolved in solution? No, not very much at all. Not very much at all. Basically, we would say it's insoluble. Now, there's probably a little tiny bit of ion in a solution. We're not going to say that it, none of it will go into solution. Very little of it is there. Okay, let's try another problem. Let's try, what's my time? I think we can do it. Okay, the KSP for copper 2 iodate which is Cu IO3 2 is 1.4 times 10 to the minus 7th. So still we've got our equilibrium line to the left, but it's certainly more soluble than that bismuth sulfide. At 25 degrees Celsius. Calculated solubility. At 25 degrees Celsius. Okay, now if we are looking for solubility, what are we solving for in our ice diagram? We are solving for x. We are trying to find x, because remember, x represents solubility. Okay, so let's first of all write the equation. So we've got Cu so copper 2 iodate going to copper 2 plus, and this is aqueous, what's this thing? It's a solid. And iodate, 2 iodates. And those are -1 charge, and that's aqueous. Okay, so there it is. Let's write the KSP. So KSP is equal to, or let's write the equilibrium expression, I'm sorry. See, there I go, it's like doing it up above again. Okay, Cu 2 plus, and then IO3 minus, and that quantity is squared. Okay, I know that, and I'm trying to find x. So, if we make an ice diagram here, I, C, 0, 0, plus x plus what? 2x. So I have x and I have 2x. So when I plug that into my equilibrium expression, I'm going to end up having, what's my KSP? 1.41, sorry, this pen is a little bit tricky today. It's not going where I want it to go. So our KSP is 1.4 times 10 to the minus 7th. Ooh, this side of the board doesn't do well with the pen. Is equal to, what do I have here? X times 2x squared. X cubed. So from that, right, so I've plugged in x, 2x, which gives me 4x cubed. Can you find the value of x here? So what are we going to do? We're going to divide both sides by 4, and then we're going to find the cube root of here, and we end up getting an x value that is 3.3, try this on your calculator, times 10 to the minus 3rd. 3.3 times 10 to the minus 3rd. Okay, so now how do we write that as our answer? So that means that the solubility is 3.3 times 10 to the minus 3rd moles per liter at 25 degrees Celsius. So for every liter of solution, for every liter of water, we can get 3.3 times 10 to the minus 3rd moles of copper 2 iodate dissolved in solution. That's how much we can get into solution. All right, we're done.